The curtain of mist rises from the valley floor as the first light of dawn breaks over the horizon. Droplets of water cling to every blade of grass, every leaf, every spider web woven between branches. In the distance, clouds gather along the ridgeline, their undersides tinged pink by the rising sun. As the air warms, the mist begins to dissipate, rising upward until it vanishes from sight. This daily miracle, so common we rarely pause to consider it, represents one of the most fundamental and powerful forces shaping our world. Dr. Rachel Evans stands at the edge of the research station's observation deck, her eyes tracking the movement of clouds across the valley. For 30 years, she has studied the invisible choreography that directs every raindrop, every snowflake, every hurricane that has ever formed on Earth. A meteorologist by training, her career has evolved to encompass climate science, physics, and planetary studies, all in pursuit of understanding the complex dance that creates our weather. Most people think of gravity when they consider the forces that shape our world. Rachel says, her gaze still fixed on the distant mountains. But there's something even more fundamental at work in our atmosphere, something that drives every weather pattern you've ever experienced. That force is the uneven heating of Earth by the sun, the engine behind global atmospheric circulation. This seemingly simple concept, that the sun heats different parts of our planet differently, drives a complex system of air movement, moisture transport, and energy distribution that defines our climate, shapes our landscapes, and has influenced the evolution of all life on Earth. It is responsible for everything from the gentle summer shower watering your garden to the devastating power of a Category 5 hurricane. To understand how this invisible force works, we must first journey 93 million miles from Earth to examine our sun, the ultimate source of nearly all energy on our planet. The sun is an almost perfect sphere of hot plasma, approximately 864,000 miles in diameter, so vast that more than 1 million Earths could fit inside it. At its core, nuclear fusion converts hydrogen into helium at temperatures of about 27 million degrees Fahrenheit, releasing the energy that eventually reaches us as sunlight. This energy travels outward through the sun's layers before being radiated into space as electromagnetic radiation, including visible light, ultraviolet light, and infrared radiation. Each second, our sun produces enough energy to power human civilization for almost 500,000 years at current consumption rates. Of that vast output, Earth intercepts only a tiny fraction, about 1 part in 2 billion. Yet this is still enough to drive every weather system on our planet. The journey of solar energy to Earth is just the beginning of the story, explains Dr. Quincy Wilson, a physicist who specializes in atmospheric thermodynamics at the National Center for Atmospheric Research in Boulder, Colorado. What happens next, how that energy is distributed, absorbed, and reflected, is what creates the astonishing complexity of Earth's weather. When solar radiation reaches Earth, approximately 30% is immediately reflected back to space by clouds, atmospheric particles, and reflective surfaces like snow and ice. This reflectivity, called albedo, varies significantly across our planet's surface. Fresh snow can reflect up to 90% of incoming solar radiation, while dark forests might reflect as little as 10%, absorbing the rest as heat. The open ocean, which covers more than 70% of Earth's surface, absorbs about 94% of the solar energy that reaches it. The remaining 70% of solar energy that is not immediately reflected is absorbed by land, oceans, and the atmosphere itself. This absorbed energy is converted to heat, warming the air, land, and water. But this warming does not happen uniformly across the planet, and this inequality is the key to understanding global weather patterns. Earth's spherical shape means that sunlight strikes the equator almost directly but hits the poles at an oblique angle. As a result, a square meter of land at the equator receives far more solar energy than a square meter at higher latitudes. This differential heating creates a fundamental imbalance. The equatorial regions receive an energy surplus, while the polar regions experience an energy deficit. Nature abhors imbalance, Rachel explains, as we walk along the ridge above her research station. Physics demands redistribution. The entire global circulation system exists to move heat from where there's too much to where there's too little. This redistribution happens through both atmospheric circulation, weather, and oceanic circulation, currents. The atmosphere and oceans work together as Earth's heat distribution system, transporting energy from the tropics toward the poles in a never-ending attempt to equalize temperatures across the planet. At its most basic, this circulation creates three major atmospheric cells in each hemisphere: the Hadley cell nearest the equator, the Ferrel cell in the mid-latitudes, and the polar cell at high latitudes. These cells are massive rivers of air that move heat and moisture around the planet in predictable patterns. The Hadley cell begins with hot, humid air rising near the equator. As this air rises, it cools and loses its moisture as precipitation, creating the rainy tropical climate characteristic of regions like the Amazon basin, Central Africa, and Southeast Asia. After releasing its moisture, the now dry air moves poleward at high altitudes until it reaches about 30 degrees latitude, north or south, where it descends. This descending air creates persistent high-pressure zones that are responsible for most of the world's great deserts. The Sahara, the Arabian, the Kalahari, and the Australian outback all sit near 30 degrees latitude, precisely where the Hadley cell brings dry air back to Earth's surface. The relationship between these circulation cells and Earth's great deserts is not coincidental, says Dr. Miguel Sanchez, a climatologist who has studied the expansion of arid zones under climate change. It's a direct result of physics, specifically, the physics of air movement and moisture transport driven by differential heating. From these high-pressure zones at 30 degrees latitude, some air returns toward the equator along the surface, completing the Hadley cell. These surface winds, the famous trade winds that powered sailing ships for centuries, do not blow directly north and south because of another effect: Earth's rotation. As our planet spins on its axis, completing one rotation every 24 hours, it creates an apparent force called the Coriolis effect. This effect causes moving objects, including air masses, to appear to deflect to the right in the northern hemisphere and to the left in the southern hemisphere. The Coriolis effect is zero at the equator and increases with latitude, reaching its maximum at the poles. The Coriolis effect transforms what would otherwise be simple north-south air movements into the complex wind patterns we observe. The equator-bound surface winds of the Hadley cell become the northeast trade winds in the northern hemisphere and the southeast trade winds in the southern hemisphere. Similarly, the poleward-flowing surface winds of the Ferrel cell, between approximately 30 and 60 degrees latitude, become the prevailing westerlies that dominate weather patterns in North America, Europe, and parts of Asia and the southern hemisphere. The Coriolis effect is why hurricanes spin counterclockwise in the northern hemisphere and clockwise in the southern hemisphere, Rachel explains. It's why ocean currents form circular patterns called gyres. It's why jet streams flow west to east instead of directly toward the poles. Understanding the Coriolis effect was a breakthrough in meteorology that finally allowed us to make sense of global wind patterns. These global wind patterns are not merely academic curiosities. They directly control the distribution of rainfall, the formation of storms, and the seasonal changes we experience throughout the year. They determine which regions will be fertile and which will be desert, which will experience frequent floods and which will suffer chronic drought. As Earth orbits the Sun, the tilt of its axis, currently about 23.5 degrees, causes the most direct solar radiation to migrate north and south of the equator with the seasons. This annual migration shifts the entire atmospheric circulation system, bringing the rainy conditions of the intertropical convergence zone, where the Hadley cells of the northern and southern hemispheres meet, into tropical regions during their respective summer seasons. This seasonal shift creates the monsoons that deliver life-giving rain to places like India, Southeast Asia, and parts of Africa and the Americas. The Asian monsoon, one of the most dramatic examples of this phenomenon, affects the lives of nearly half the world's population. When the intertropical convergence zone shifts northward during northern hemisphere summer, it draws moisture-laden air from the Indian Ocean over the Indian subcontinent, unleashing torrential rains that sustain agriculture across the region. The predictable timing of monsoons allowed ancient civilizations to develop complex agricultural systems, notes Dr. Ananya Patel, a historical climatologist at Oxford University. The Indus Valley Civilization, ancient Egypt along the Nile, and Mesopotamia between the Tigris and Euphrates, all relied on seasonal rainfall patterns determined by global atmospheric circulation. Yet these same circulation patterns can also bring destruction. Hurricanes, typhoons, and cyclones, different names for the same phenomenon in different parts of the world, form over warm ocean waters in specific regions determined by global circulation patterns. These massive storms, among the most powerful forces in nature, develop when warm ocean water, typically above 80 degrees Fahrenheit or 27 degrees Celsius, evaporates and rises, creating an area of low pressure. As more warm, moist air is drawn into this low-pressure zone, it too rises and cools, causing the water vapor it contains to condense into clouds and precipitation. This condensation releases heat, warming the air and causing it to rise still faster, drawing in more warm, moist air in a self-reinforcing cycle. The Coriolis effect causes this rising air to spin, forming the characteristic spiral pattern visible in satellite images of hurricanes. As the storm intensifies, an eye typically forms at its center, a region of calm, descending air surrounded by the most powerful winds in the system. A mature hurricane is essentially a heat engine, explains Dr. Carrie Emanuel, a meteorologist at the Massachusetts Institute of Technology who pioneered the theory of hurricane intensity. It converts the heat energy of warm ocean water into the mechanical energy of wind. The physics is similar to that of a steam engine or a power plant, but on a vastly larger scale. This heat engine can generate extraordinary power. The average hurricane releases energy equivalent to 600 trillion watts, about 200 times the worldwide electrical generating capacity. During its lifetime, a typical hurricane might release as much energy as 10,000 nuclear bombs. Yet hurricanes, for all their destructive potential, are part of Earth's heat distribution system. They efficiently transport heat from the tropics toward the poles, helping to balance global temperatures. Without these storms and other components of the global circulation system, the tropics would be significantly hotter and the polar regions even colder than they are today. The circulation patterns that drive hurricanes also influence another crucial element of our weather: jet streams. These fast-flowing, narrow air currents found near the boundary between the troposphere and stratosphere flow primarily from west to east due to the combined effects of atmospheric heating and the Coriolis force. The polar jet stream, which typically flows at altitudes between 25,000 and 35,000 feet at speeds that can exceed 250 miles per hour, acts as a boundary between cold polar air to the north and warmer mid-latitude air to the south in the northern hemisphere, with the pattern reversed in the southern hemisphere. The position and strength of this jet stream directly influence weather patterns across North America, Europe, and Asia. When the jet stream follows a relatively straight path, it keeps cold air confined to the north and warm air to the south. But when it develops large meanders, called Rossby waves, it can allow Arctic air to plunge deep into typically temperate regions, causing cold snaps, or pull warm tropical air far northward, creating unseasonable heat. The jet stream is like a fence between different air masses, Rachel says, sketching a wavy line on her notepad. When that fence develops big bends, weather gets interesting, sometimes dangerously so. The behavior of the jet stream is intimately connected to the temperature difference between the Arctic and mid-latitudes. As the Arctic warms more rapidly than lower latitudes, a phenomenon called Arctic amplification, this temperature difference decreases, potentially leading to a weaker, wavier jet stream that allows extreme weather to persist for longer periods. We're conducting an unprecedented experiment with Earth's atmosphere, Rachel notes. By changing the energy balance through greenhouse gas emissions, we're altering the very circulation patterns that have shaped human civilization for thousands of years. The circulation systems that define our weather do not operate independently of Earth's other major systems. They interact intimately with the oceans, which store vastly more heat than the atmosphere and move that heat through currents that operate on much longer timescales than atmospheric circulation. The Gulf Stream, part of the Atlantic meridional overturning circulation, transports warm water northward from the Gulf of Mexico along the eastern coast of North America before crossing the Atlantic to warm Western Europe. This current alone moves more than 100 million cubic meters of water per second, about 100 times the combined flow of all the world's rivers, and delivers an enormous amount of heat to the North Atlantic region. London sits at the same latitude as Calgary, Canada, yet has a much milder climate, points out Dr. James Hansen, a climatologist known for his early warnings about climate change. That difference is largely due to ocean circulation bringing warm water from the tropics to Western Europe. Ocean circulation and atmospheric circulation are linked in complex feedback loops. The El Niño Southern Oscillation, ENSO, perhaps the most significant of these ocean-atmosphere interactions, alternates between El Niño conditions, warmer than average surface waters in the eastern equatorial Pacific, and La Niña conditions, cooler than average waters in the same region. During El Niño events, the trade winds that normally blow from east to west across the tropical Pacific weaken or even reverse, allowing warm water that typically accumulates in the western Pacific to flow eastward. This shift in ocean temperature alters atmospheric circulation patterns, changing rainfall across much of the tropics and influencing weather as far away as North America, Europe, and even Antarctica. El Niño is a perfect example of how the ocean and atmosphere work as coupled systems, explains Dr. Kevin Trenberth, a climate scientist who has studied ENSO for decades. Changes in one inevitably affect the other, often in ways that propagate around the globe. These teleconnections, influences that extend far beyond the region where a change originates, are a key feature of Earth's climate system. They explain why drought in Australia might be linked to ocean temperatures near Peru, or why rainfall patterns in Africa can be influenced by sea surface temperatures in the Indian Ocean. The differential heating that drives these global circulation patterns also creates local weather phenomena that shape our day-to-day experience. Consider the sea breeze that provides relief on hot summer days in coastal areas. During daylight hours, land heats more quickly than water because soil and rock have a lower heat capacity than the ocean. This temperature difference creates a pressure gradient, lower pressure over the warmer land, higher pressure over the cooler water, that draws air from sea to shore. At night, the process often reverses. Land cools more quickly than water, creating a temperature gradient that draws air from land to sea, the land breeze. This daily cycle of heating and cooling, pressure changes, and air movement is a miniature version of the global circulation patterns that operate on a planetary scale. Similar processes create mountain and valley breezes in areas of varied terrain. During the day, mountain slopes heat more quickly than valleys, causing air to rise up the slopes. At night, the pattern reverses as the mountain slopes cool more rapidly, causing air to flow downhill into the valleys. On a larger scale, monsoon circulations operate on the same principle of differential heating between land and sea, but on a seasonal rather than daily time frame. During summer, the Asian landmass heats more rapidly than the Indian Ocean, creating a pressure gradient that draws moisture-laden air from sea to land. During winter, the pattern reverses, with dry air flowing from the cooler land to the warmer ocean. These patterns of heating and cooling, rising and sinking air, are the heartbeat of our atmosphere, Rachel says. They create the winds that disperse seeds, the rains that fill rivers, the snow that builds glaciers, and the storms that reshape coastlines. The uneven heating of Earth does more than drive weather patterns. It also creates the conditions necessary for life as we know it. Consider the water cycle, the continuous movement of water between the atmosphere, land, and oceans. Solar energy evaporates water from oceans, lakes, rivers, soil, and plants. This water vapor rises with warm air, eventually cooling and condensing to form clouds. Under the right conditions, these clouds release their moisture as precipitation, returning water to Earth's surface where it may infiltrate the soil, flow as runoff into rivers and eventually oceans, or be taken up by plants and released back to the atmosphere through transpiration. This cycle, driven entirely by differential heating, distributes fresh water across continents, enabling terrestrial life. Without it, rain would not fall inland, rivers would not flow, and most land would be as barren as the driest deserts. The water cycle also transports energy. When water evaporates, it absorbs heat, specifically the latent heat of vaporization, about 2,260 kilojoules per kilogram of water. This heat remains stored in the water vapor as it rises and moves with air currents. When the vapor condenses back to liquid water in clouds, this heat is released, warming the surrounding air. This process moves an enormous amount of heat from Earth's surface to the atmosphere, explains Dr. Susan Trumbore, a biogeochemist at the Max Planck Institute for Biogeochemistry. About 25% of the solar energy absorbed at Earth's surface is used to evaporate water. That energy is later released in the atmosphere when the water vapor condenses. This latent heat transfer is a major component of Earth's energy budget and a key factor in weather development. The release of latent heat provides much of the energy that drives thunderstorms, fuels hurricanes, and powers large-scale atmospheric circulation. The uneven heating of Earth also drives ocean currents through both direct thermal effects and by powering the winds that create surface currents. These currents distribute heat, nutrients, and dissolved gases throughout the world's oceans, supporting marine ecosystems and influencing climate. In the Atlantic Ocean, for instance, warm surface water flows northward, gradually releasing heat to the atmosphere before cooling, becoming denser, and sinking in the North Atlantic. This deep, cold water then flows southward, eventually upwelling in the Southern Ocean and elsewhere, bringing nutrient-rich water back to the surface where it supports phytoplankton blooms that form the base of marine food webs. This thermohaline circulation, driven by differences in temperature and salinity, is like a conveyor belt that has been running for millions of years, says Dr. Wallace Broecker, the oceanographer who coined the term global conveyor belt to describe this system. It's essential for distributing heat, oxygen, and nutrients throughout the world's oceans. Even the distribution of life on Earth reflects the influence of differential heating and the circulation patterns it creates. The remarkable biodiversity of tropical rainforests exists in large part because these regions receive abundant rainfall and solar energy, a direct result of their position within the rising branch of the Hadley cell. The sparse vegetation of desert regions at around 30 degrees latitude is similarly tied to their location beneath the descending, dry air of the same circulation cell. Mountain ranges interact with atmospheric circulation to create rain shadows, areas of reduced precipitation on the leeward side of mountains. As air rises up the windward side of mountains, it cools, causing water vapor to condense and fall as rain or snow. The air that continues over the mountain has less moisture, creating drier conditions on the leeward side. The Great Basin Desert of the western United States exists largely because the Sierra Nevada mountains capture moisture from Pacific air masses before they can reach the interior. Similar rain shadow effects create dry regions downwind of the Andes, the Himalayas, and other major mountain ranges. The distribution of ecosystems across Earth is not random, Rachel explains. It's a direct response to the patterns of energy and water distribution created by differential heating and atmospheric circulation. These patterns have shaped human history as well. Ancient civilizations typically developed in regions with reliable water sources and predictable weather, conditions determined by global circulation patterns. The earliest agricultural societies emerged in river valleys where seasonal flooding delivered both water and nutrients to farmland, often in regions influenced by monsoon cycles or other predictable precipitation patterns. Trade routes developed along paths where prevailing winds made sea travel efficient, while barriers to movement often coincided with climate transitions created by circulation patterns. The distribution of diseases, agricultural potential, and even cultural practices shows the imprint of climate patterns driven by differential heating. The story of human civilization is, in many ways, a story of adaptation to the opportunities and constraints created by atmospheric circulation, notes Dr. Jared Diamond, author of Guns, Germs, and Steel, a Pulitzer Prize-winning examination of environmental influences on human societies. As our understanding of atmospheric circulation has grown, so has our ability to predict weather and climate. Modern weather forecasting began in the mid-19th century but made relatively little progress until the advent of computers allowed meteorologists to solve the complex equations governing atmospheric motion. The first numerical weather prediction was performed in 1950 by a team led by Jules Charny and John von Neumann using ENIAC, one of the world's first electronic computers. Their 24-hour forecast took about 24 hours to calculate, making it of limited practical use but demonstrating the principle that weather could be predicted through mathematical modeling. Today's weather models incorporate data from satellites, weather stations, aircraft, ships, and other sources to create a three-dimensional picture of the current state of the atmosphere. Using the laws of physics, specifically fluid dynamics and thermodynamics, these models project how this state will evolve over time, producing forecasts that extend days or even weeks into the future. The improvement in weather forecasting over the past few decades has been extraordinary, says Dr. Louis Uccellini, former director of the National Weather Service. A 5-day forecast today is as accurate as a 3-day forecast was in the 1990s. This improvement has saved countless lives and billions of dollars by allowing better preparation for extreme weather events. Climate models operate on similar principles but focus on longer timescales and include more components of the Earth system, such as oceans, ice sheets, and the carbon cycle. These models have successfully reproduced past climate changes and provided insights into how human activities are altering the climate system. The fundamental physics of atmospheric circulation is well understood, Rachel emphasizes. We know that adding greenhouse gases to the atmosphere traps more heat, altering the energy balance that drives circulation. The uncertainty is not whether climate change is occurring, but precisely how circulation patterns will adapt to this new energy balance. As greenhouse gas concentrations increase, the atmosphere retains more heat, but this additional energy is not distributed evenly. The Arctic is warming about twice as fast as the global average, a phenomenon called Arctic amplification, largely because melting sea ice reveals darker ocean water that absorbs more solar radiation. This disproportionate warming is changing the temperature gradient between the equator and poles that drives atmospheric circulation. Some studies suggest that these changes are already affecting the jet stream, making it wavier and more prone to creating persistent weather patterns that can lead to prolonged heat waves, cold spells, droughts, or flooding. We're pushing the climate system into uncharted territory, warns Dr. Michael Mann, a climate scientist at the University of Pennsylvania. The circulation patterns that have shaped our civilizations are changing more rapidly than at any time in human history. The water cycle is intensifying as well. Warmer air can hold more moisture, about 7% more for each degree Celsius of warming, leading to more extreme rainfall when conditions are right for precipitation. Meanwhile, enhanced evaporation can worsen droughts in regions experiencing water stress. These changes are not uniform across the globe. Some regions are becoming wetter, others drier. Some are experiencing more variable precipitation, with longer dry periods interrupted by more intense rainstorms. These shifts in precipitation patterns, driven by changes in atmospheric circulation, have profound implications for agriculture, water resources, and ecosystems. Ocean circulation is changing too. There is evidence that the Atlantic meridional overturning circulation, which includes the Gulf Stream, has weakened by about 15% since the mid-20th century. Further weakening could significantly alter climate patterns in North America and Europe, potentially making Western Europe cooler even as global temperatures rise. The climate system is full of potential tipping points and feedback mechanisms, Rachel explains. Changes in circulation can amplify or dampen warming, shift precipitation patterns, and alter the frequency and intensity of extreme weather events. Despite these complexities and uncertainties, the fundamental relationship between differential heating and atmospheric circulation remains unchanged. The sun still heats the equator more than the poles, creating a temperature gradient that drives global air movement. Air still rises where it's warm and sinks where it's cool. The Coriolis effect still deflects moving air masses based on latitude and Earth's rotation. What is changing is the energy balance that influences how these processes operate. By adding greenhouse gases to the atmosphere, human activities are altering the flow of energy through Earth's climate system, creating what Rachel calls a new normal for atmospheric circulation. We're conducting an experiment with the only atmosphere we have, she says. The physics is clear: change the energy balance and you change circulation patterns. Change circulation patterns and you change weather. As we conclude our visit to the research station, Rachel leads us to a small clearing where instruments measure atmospheric conditions. A weather balloon is being prepared for launch, its payload of sensors designed to sample temperature, humidity, pressure, and wind speed at different altitudes. Each data point helps us understand the system better, Rachel explains as the balloon rises into the blue sky. Each measurement improves our models, refines our forecasts, and deepens our understanding of how differential heating drives the atmospheric engine. The balloon grows smaller against the backdrop of gathering clouds. In the distance, rain falls from dark thunderheads, while closer to the horizon, sunlight breaks through in golden shafts. The entire scene, clouds, rain, sunlight, wind, represents the invisible force of differential heating made visible through its effects on our atmosphere. Everything you see, every cloud, every raindrop, every breeze, exists because the sun heats our planet unevenly, Rachel says. This simple fact creates the incredible complexity of Earth's weather and climate systems. As we depart, the first raindrops begin to fall, completing a journey that began with evaporation over a distant ocean. Driven by the sun's uneven heating of our planet, the water will return to the soil, flow to rivers and eventually the sea, only to begin the cycle again. Part of the endless circulation that makes Earth not just habitable, but extraordinarily vibrant with life. This cycle, powered entirely by the differential heating of our planet, has shaped landscapes, guided evolution, and influenced human civilizations throughout history. It continues today, modified but not fundamentally changed by human activities, an invisible force that controls every weather pattern on Earth. The next time you feel a breeze against your face, watch clouds build into a summer thunderstorm, or shelter from winter snow. Remember that you are experiencing the effects of the most fundamental force in our atmosphere, the uneven heating of Earth by the sun. This invisible force has shaped our world and will continue to do so long into the future, even as we alter the delicate energy balance that has defined Earth's climate for millennia.